So sorry about that, it got disconnected. Let me check whether it is connecting or not. One second. Okay, sorry about that, it got disconnected again. Okay, so we were dealing with the rectangle, and we are going to find out per unit width. So for per unit width, we can write our f each, and this is our per unit width will be equal to rho L G upon 2, and this is cot of theta. And from here we can write that our total horizontal compressive force will be equal to our F total per unit width will be equal to, this will be twice of F each per unit. So this comes as rho L G, and we have this as cot of theta. And once again we are going to find out our this maximum and minimum value of theta, and for that we are going to consider F each equation. So we can say our F each for per unit width is our rho L G upon 2 and cot of theta. So maximum minimum we can easily differentiate it. So we can write this as df each of W for our theta will be equal to, this will be coming as rho L G upon 2, and we have cot of theta, and giving us minus cosec square theta. And therefore, and we can write this as our for theta less than pi by 2 but greater than 0. And from here we can also draw a conclusion that our F each per unit width is strictly decreasing on 0 and pi by 2. So it is quite easy conclusion from the trigonometric itself, and therefore we can say that we can also write that the minimum on the closed interval is at theta is equal to pi by 2, because we get our cot of theta will be coming as equal to 0. Therefore we can write that our F each for per unit, its minima will be equal to 0 at theta is equal to pi by 2. Okay. But for our this maximum value, you can say calculate it by using a little bit a different approach. So we can say there is no finite interior maxima, okay, which basically means that the horizontal force increases without bound as theta tend to 0 positive, okay, because this cot of theta rather will be going to infinity. Okay. We can say that because cot of theta will tends to infinity. Thus, we can say the we can write the super is plus infinity as theta tend to 0 positive. So this is a little bit tricky, but we get the rough approximate idea with respect to the value of 0. Okay. Now we come to a part C, and in part C we are given a circular disc. Okay. So the circular disc, so we have two cylinders. This is the first cylinder, the second cylinder, and a circular disc is placed something like this. So once again we are having 2 points of contact. This is P1 and this is our P2. Okay. So whatever figure is there, whatever shape is there, these 2 points of contact will be always there, whether it is triangle or whether it is rectangle. And we are given that this is having a radius of our A. Thus we can say its area, our A will be equal to pi A square. Now from here we can easily calculate its mass. So we can say its mass, that is M, is rho times A. It comes as pi rho A square. Okay. And now we come to the force of each. So you can say force, compressive force of one side F each. Its general formula we have already derived, that is mg by 2, and we have cot of theta. Now we substitute value of m. So this gives us our pi rho A square g upon 2 and cot of theta. Similarly, now we can find out the total. So we can say our total compressive force, that is our Ft, is equal to twice F each. We have also derived this formula. Therefore, we can say that our Ft will be equal to 2 multiplied by pi rho A square g 2 cot of theta. And this 2 and 2 cancels out. So this comes as equal to our pi rho a square g cot of theta. Okay. Now once again we come to its maximum and minimum value. So we are going to consider this f each. So we can say that our f each is our rho pi a square g 2 cot of theta. Okay. And this same we find out its derivative, and its derivative will be coming equal to as minus, and we have this as rho pi a square g upon 2, and this comes as our cosec square theta. Okay. And this will be our less than 0 on 0 to pi by 2. Okay. And like we discussed in this previous case, for the rectangle, same analysis we can draw it here or repeat it. Okay. So we know that our f is strictly decreasing with theta. Therefore we are going to have a supermum, and that will be a plus of infinity at, not at, but as theta tend to 0 positive. Okay. So it means there is no finite interior maxima. Okay. So here supermum basically means that there is no finite interior maxima, because as soon as we put theta equals 0, cot goes away. Okay. And for our minima, which is our f minima, and that f minima will be 0 at theta is equal to pi by 2. Okay. That is quite obvious from the cot of pi by 2. So this was our first question. We come to the second question. Okay, it states that a uniform flexible rope of length L hangs vertically under gravity. The rope has a constant linear mass lambda, that is mass per unit length. Let y be the vertical coordinate measured downward from the top end of the rope. Find the tension T of y in a rope at a point located at a distance y below the top. Express your answer in y, L, lambda and g. And this is comparatively easy question. Only the language is a little bit typical, otherwise it is quite straightforward. Okay, so we are given that this is our ceiling, and from here we have a rope, and L is the length of the rope, and it says that there is a point y. Okay, so let us suppose this is a y and at a distance y from the top. So it means the bottom length left will be our L minus y, and at this particular point the tension is given as T of y, okay, which we are supposed to find out. And so here we have to remember that the tension at the height y must support the weight of the rope below that point. Okay, it means all the weight below this point will be supported by this tension. So this is an important part here. Rest is quite simple to sort it out, and therefore we can say the tension at y must support the weight of the rope below that point. Below that point. And like we said that the below point is having a length of L minus Y and the density is given as lambda. Therefore we can say that the mass below point Y will be equal to L minus Y multiplied by lambda. Okay. And therefore we can find out its weight. So we can say that weight of the segment will be equal to, let us suppose that is our W will be equal to our, this is our lambda G L minus Y. Okay. And like I said, this weight is to be supported by the tension at that point, and the tension at that point is given as T of Y. Therefore we can say that our T of Y will be equal to lambda G L minus Y, and this is we calculated. We can just also sort it out. We can say that if value of Y is equal to 0, okay, then we can get the tension at 0 will be maximum, that is lambda GL, and when Y is equal to L, we get our T of L will be equal to 0. Okay, it's meaning tension at the free end at the bottommost point will be 0, and at the top it will be maximum, that is our lambda GL. And if you want to measure from the bottom side, we can also measure it from the bottom side, okay, the point. Next question. It states that a uniform rope of length L and linear mass density lambda lies on a rough plane inclined at an angle of theta above the horizontal. The upper end of the rope is fixed to the plane by a nail. The coefficient of friction between the rope and the plane is mu. Determine all possible values of tension at the top end of the rope that are consistent with the static equilibrium. So we have to find out the all possible values. Okay. And this is ideally it should have written in the question itself, explained, because it is asking for all possible values, but there are certain conditions which are to be fulfilled, and this all possible values will be dependent upon how we are going to place the rope on the slope. Okay, that will be defining the all possible values. We come to that later on, and for the sake of simplicity we can just draw the figure. So this is our slope at angle of theta, and on which a rope is placed, and the top end is having a nail. Okay, so this is a nail. With the help of nail it is fixed, okay, and we have to find out, and the coefficient of friction is lambda, and linear density is mu, and density is linear mass density is lambda, length is L. So you can see our mu's, and this is our L. Okay. So in this case, so let us start with the simplest portion which simplest option which comes to our mind, and for that we can easily say that there will be a mg acting in the downward direction, okay, and mass mg will be our lambda lg, so we can put this as lambda lg, which can divide into two components, and there will be a normal over n. So this will be for theta, so we get this as lambda lg cos of theta, and this is our lambda lg sine of theta. And so we can just write that it's two component, so we can say that our weight has two components. One be our parallel component that will be down the inclined plane, so let us call this a W parallel, that is our lambda lg sine of theta, and other component will be our normal, that is our lambda W perpendicular is our lambda lg cos of theta, and that will be also equal to our normal. And we know that this for the friction can be either acting down the inclined plane or it can be acting up the inclined plane. These are the two options only. Okay. So we can say that our static friction can act up or down the plane, but whatever direction it is acting, the maximum its magnitude will be fixed. So we can say its maximum magnitude, that is our F max, will be equal to our mu times n, and this comes as mu lambda L G, and we have our cos of theta. Okay. And the first thought which comes to us is that the rope is simply lying on the plane. Okay. So if the rope is simply lying on the plane, okay, so this is the first straightforward option that comes to our mind. So we start from there only. So we can say that our rope is just lying on the plane. Okay. So it means the total down plane force, will be nothing but our lambda Lg, and we have our sine of theta. And obviously friction will be in the opposite direction. Therefore we can say that friction acts up plane. And its value is our mu times lambda Lg cos of theta. Therefore, suppose excuse me. So we were having a rope. Okay, so this is our rope, and this is our nail. Okay. So we are having a force that is in downward direction, and we have a friction that is our upward direction. Therefore, we can say that our tension at the top means at the nail. Therefore, we can say the tension at the top will be equal to our down this force, we call this as W parallel, and this is our frictional force. So we get this W parallel minus F, which comes up with lambda L G sine of theta minus mu lambda G cos of theta. Okay, so this is one of the possible cases. Okay, and second case, which we can just also discuss, is that, or we can put it in this way, that our basically everything will be dependent upon the direction of our static friction, and we have to remember that the static friction is history dependent. Okay, so this is a key term in this question. So we have to remember that our static friction is history dependent. Okay, so in this particular case, the history is how we are going to place the rope. Okay, so like in first case, we discussed that rope is simply lying there on the slope. Okay, so that is the history of that, and based on this we were able to find out the friction. Okay. And so let us consider our three ways in which this history can be discussed. Okay, so we can say that our three physically distinct ways the rope can be placed. The rope can be placed. And one second. And so the first case is our rope is laid gently. Rope is placed gently, which basically means no stretching. So it means it has a tendency to slide downward. You can say tends to slide down. Okay, so it means our friction, this will be up the plane. So we have the friction, that is our up the plane, and therefore we can say our tension T will be equal to lambda L G sine of theta minus F, and we know that our value of F is greater than 0 but less than mu lambda L G, and this is our cos of theta. Okay. So it means the minimum possible value, you can say that our minimum possible value of the tension, that's the T minimum, will be equal to our lambda L G sine of theta minus, and mu lambda Lg cos of theta, and this is our minimum possible value. Okay. Or we can also say that if this tension saturates to 0, then we can further write it as that we have our, unless this is negative, in which case the tension saturates at 0. Saturates at 0. So it means we can write that our T minimum will be our maximum of 0, and this is lambda Lg, and we get this as our sine of theta minus mu cos of theta. Okay, so this was our first case. Now we come to our second case, and the second case is that the rope is first stretched up the plane, then nailed. So this is our second case. So herein, like I said, that our static friction is nothing but our history dependent. Okay. So specifically, we can write that our history in this case is that rope is pulled. Rope is pulled upward before nailing. So this is our history of this. Okay. Therefore, and rope is pulled upward. Therefore, the natural tendency after release so natural tendency after release it will be that rope wants to slide up the plane. Therefore, our static friction acts down the plane. So it means, like I said, that the friction, or we can say static friction, will be our history dependent. So if we stretch the rope and then we nail it, the direction of our static friction changes. And we can write that total force down the plane. Okay. Now in this case, if this is our rope, we already having the weight, that's our W parallel in the downward direction, and now we are also having friction in the downward direction. Okay. Therefore, we get the total force down the plane will be equal to our W parallel plus F, and that is our lambda LG sine of theta and plus F. And we already know that our F should be less than equal to 0 and greater than 0 and less than our mu lambda LG cos of theta. And therefore, for equilibrium, we can write our tension T will be equal to our lambda LG sine of theta plus the value of the friction, that is mu lambda LG cos of theta. And this is nothing but our maximum possible value of the tension. So we can say our T max, we can take lambda LG as common, and we get this our sine of theta plus mu cos of theta. Okay. And finally, we come to our third case, and in third case what we do, we simply place the rope on the frictionless plane. Okay. So we can say rope is placed on frictionless plane and then turned on. So which basically means here as per our history, the plane is our frictionless, therefore we can say that our mu is equal to 0. Okay. And our rope is placed, comes to rest. Okay. And now, like I said, the friction is turned on, so we can write it as that magically we can write it as friction is turned on means mu is equal to 0, and this is without disturbing the rope. Okay. So it basically means that this is our slope, and on this we first place our rope. Okay. And when we first placed our rope, the value of mu is equal to 0, and after some time this rope comes to a rest, and after the rope comes to the rest, we turned friction on. Now the friction is not equal to 0. Okay. So this is a basic premise of this entire discussion. Okay. And we already know, one second. And we know that our friction is self-adjusting. So no, since friction is self-adjusting, and requires a desire to move. And basically it means that the friction is always there, but if nothing is moving, the friction will be idly, that it is not present. This is meaning that desire to move. And like we said, that the rope is not tending to move at that instant. So it means the value of friction that will be acting will be equal to 0. And if the value of friction acting is equal to 0, the tension T will be nothing but our mu Lg sine of theta. And now we can write all the possible range of the tension which we calculated. So we can say that our static friction can vary from, we have our minus mu lambda Lg cos of theta, that is our down plane, to plus mu Lg cos of theta up plane. And if we look closely, this is nothing but our plus minus mu times n. So value of the friction is going to vary between plus minus mu of n, where n is our this normal value. Therefore we can write that our T minimum will be equal to our maximum value from 0 and lambda Lg sine of theta minus mu cos of theta, and T maximum is equal to our lambda Lg sine of theta plus mu cos of theta. Or in simpler terms, we can write that our tension T belongs to our max 0 comma lambda Lg sine of theta minus mu cos of theta, and lambda Lg sine of theta plus mu cos of theta. So these were the maximum and, or we can say, the range of the tension that can be found out, and it only depends upon the how the rope is being placed, or we can say the history of the rope. Okay, so we have to remember that our static friction is history dependent, and here history is the representation how we deal with our rope. Okay, so we discussed 3 cases, and in all these 3 cases the rope is placed differently. Okay, and the placement of the rope is going to define our tension. Okay. And more or less this particular aspect should be mentioned in the question, but where the question was given, this thing was not mentioned, that we have to take all the aspect in the question. It was simply mentioned that we have to find out the all possible values. That was only mentioned. And in normal case, we consider that the rope is simply lying there and moving, the friction is acting in opposite direction. That is our normal tendency to solve the question. But here we discussed it into 3 parts, and in 3 parts we discussed how differently the rope can be placed on the slope. Okay, so the placing of the rope on the slope is ultimately going to decide how the tension should be changing or how the tension is going to behave. And but ultimately the tension range will be always between our plus and minus mu n, okay, where n is the normal, and we know that normal is a perpendicular component which usually come to the cosine of our weight, that is the cos of the theta. So this completes all the 3 questions. Thank you.